Greetings, everyone. Welcome to I Get It live session webinar. Today's session is Delivering Blueprint to Brilliance. Know why mastering geometric dimensioning and tolerancing is a must for every engineer with Mark Foster. This webinar is an introduction to GD&T and will focus on what is GD&T, why you should use it, when do you want to use it, and finally, what are the advantages of using GD&T. My name is Eric Banson. I'm a content manager and SME author for I Get It here at Tata Technologies, and I'll be your host during this session. So without further ado, let's go ahead and begin. In this session today, I'll briefly walk through the I Get It website to show you exactly what we have in our offerings and give a glimpse of what to expect when you sign up. Next, we'll have Mark guide you through the fundamentals of geometric dimensioning and tolerancing, covering core principles of GD&T, such as the essential vocabulary and concepts, the application of GD&T as it has implementation across various stages of the production process from design to manufacturing and inspection. And then finally, the benefits of GD&T on how it enhances communication, minimizes errors, and guarantees quality results. Then we will close with a question and answer session with Mark. So please hold your questions until the end of the GD&T session, and please type in your question in the chat, and Mark will then be able to answer some of them. Due to time constraints, we'll have to keep the questions to a certain amount. So let's go ahead and let me move over to our website. So here we have the I Get It. When you come to myigetit.com, this is our website. And if you see here that we have across the top a course catalog, we have subscriptions. We have I Get It for Enterprise. We also have blogs with business and tech blogs. And we have an About Us page. If you kind of scroll down, you'll see that we have just a small showing of a large portion of our MCAD and PLM applications that we have to offer. And we basically we have about 2,000 plus courses. 88% of learners report career benefits, 20 plus domain topics, and we have actually 8 plus job roles. Now, when you sign up and you go in, let me show you what you see when you sign in. This is the screen you'll get. You'll see here that your welcoming screen, and you'll have courses in progress, courses completed, assessments completed, learning time. You can see the continuing learning of the courses. You have a learning path. You can also have the time spent that you have within certain courses or with assessments and things like that. If we go to our learning here, you can start to select from courses, assessments, self-learning. With the drop-down menus, you can go ahead and select all the different categories of all the different CAD offerings that we have. You can also go to your learning paths here as well. You can take a look at your history. And then you can go back and look through our catalog. Depending on what level of subscription you purchase, you'll see what types of courses that we offer in all these different CAD engineering softwares. You also have we also have quick starts, which are quick videos that get you off and learning on certain topics within each of the different CAD softwares. We also have tech tips. If you want to know just a quick tip on how to use a certain command or function, you can type it in and it will come up, and then you can actually watch. You'll have a video and then a little lesson with it. We also have then to your account, as far as a dashboard, you can have all the different types of controls to look and see how you're progressing within I Get It as well. So that basically is our website. And when you sign up for a subscription, this is, like I said, the type of thing you'll see when you go in. So let's go ahead with our, let me let's see. Let me stop sharing for a moment and let me get to the other screen. So let me go ahead and introduce our speaker, Mark Foster. He is there we go. He is a mechanical engineer with over 40 years of experience in design, quality, and geometric dimensioning and tolerancing. He has provided GD&T training for hundreds of individuals and companies, such companies as Delco Electronics, Delphi, Nissan, Caterpillar, Briggs & Stratton, and many other large corporations. We're lucky to have him here today to go through his expertise in GD&T. So let's go ahead with the webinar, and I will hand it over to Mark.
Hi, folks. I'm Mark Foster from Applied Geometrics Incorporated, AGI, where we bring your GD&T theory to reality. We've teamed up with Tata Technologies to bring you this intro to GD&T. Just what is this GD&T, geometrical dimensioning and tolerancing stuff? We want to help you make your blueprints brilliant. All right. So let's take a look at what GD&T really is. At AGI, our goal is to help people to create a higher return on their GD&T investment by communicating in a standardized way. And that's really what GD&T is all about, is communicating within a standard. We need to have a standardized way to communicate our technical requirements. And that is our mission here at AGI. So let's get right into what GD&T is. First of all, what do the words mean? Geometric. It just means the shape of something, the shape of an object. Dimensioning. Okay, you're going to put values on the shape of that object. You're going to define the nominal size and shape of that object. And then tolerancing is giving limits to those things, recognizing that it's impossible to make anything perfectly every single time. So nothing is ever perfect that we actually manufacture in the real world. And so we have to set limits on what that shape can be, and those are our tolerances. So GD&T, geometric dimensioning and tolerancing. The definition in the standard, and by the way, the standard is the ASME Y14.5, current version is 2018. That standard defines GD&T as a means of dimensioning and tolerancing a part with respect to the relationship and function of that part. Well, what does that mean exactly? Relationship and function. You know, if we think about how things fit together and we say, you know, relationship and function. Okay, relationship is how they fit together. Can they fit together? If I put two parts together and try to assemble them with some fasteners, and let me just do this so you can see it better. If I try to put this thing together and put some sort of fasteners through here to hold these parts together in an assembly, we need to understand that functional relationship, that relationship of those parts. Can I fit them together? So you can think of the relationship word here as fit. Does it fit? Do the parts fit together the way that I want them to fit? And then the function should be pretty self-explanatory, but let me explain it anyway. What is the function? Does it fit? You know, fitting together is part of the function. It can't possibly function unless it fits. It could fit and then not do what we intended it to do. That's the function part. So we have to have both. We have to have both the relationship, the fit, and the function. And GD&T gives us the means to communicate those requirements to whomever needs to know them. So ASME Y14.5 gives design the ability to communicate with manufacturing, quality, and external customers, and everybody gets to the same place. We're all on the same page. It's a language. GD&T is a language, and we use this language to encode our functional requirements into this GD&T language so that then the people that need to understand our design can decode that information and get exactly out of it what we put into it, and not just guess. Okay. And we think, well, isn't this simple? Don't we do this already with just CAD models and drawings, etc.? Well, here's an example of a CAD model or a drawing. You could do it in 2D or 3D, it doesn't matter. Pretty simple part, just a pin. And we're going to send this drawing or CAD model out to our suppliers and say, make these for us out of whatever material we say we want them made out of. Okay. So if we do that and the pins come in and they look like this pin right here, and you say, okay, well, I've got a pin and I want to make sure that I made it within the limits that were specified. I'll just measure with my handy measuring device here, and I'll measure, and I'll decide whether or not, or determine whether or not I met the print requirements. And so we think we've done a great job, and we say, yes, we believe that this pin meets the requirements, and we ship it. And the part comes in and it doesn't fit. It doesn't fit where it was supposed to fit. And that was what GD&T was supposed to be all about. You say, well, I measured it everywhere, and it measured 12 plus or minus 0.1. It was somewhere between 11.9 and 12.1 everywhere I measured it. Why wouldn't it fit? Well, because we weren't looking at how it might be bent. And people say, well, wait a minute. How, the drawing didn't show a bent pin. It showed a straight pin. Well, of course, we tried to make a straight pin, but maybe this thing gets heat treated or something else happens. And in the manufacturing process, it naturally bends a little. Well, how much is too much? Does the drawing say? I mean, some people look at this drawing and they say, absolutely, boy, this thing has got to fit in a perfect 12.1 worst case diameter hole. That's what this drawing says to me. And other people look at this and say, no, this thing doesn't say anything about how straight it has to be. It just says how big it has to be and how long it has to be, but it doesn't say how straight or how round it has to be. So some people look at this drawing and for them, it's completely clear that it means one thing. And somebody else looks at the drawing and says it's completely clear that it means something else. And it often comes down to whether you're buying or selling as to which interpretation you think makes the most sense. But if we had the pin and it ended up bent like this, and we were measuring with our caliper micrometer in those local measurements, everything was somewhere between 11.9 and 12.1. But the overall envelope that it would fit in, perfectly cylindrical envelope that it would fit in, was bigger than whatever we were measuring with our caliper micrometer. Well, just how big can it get? Well, without a standard, either interpretation would be completely correct. That's why we need a standard. We want one interpretation of what it means. And the Y14.5 standard says, yes, whatever the limit of size was, in this case 12.1, that limit is also defining a perfectly shaped, a perfectly formed envelope within which this pin must fit. Okay, so there's your fit. Right there, we now have we've imposed a rule because of a standard that we now have agreed to follow. We've imposed a rule that allows us to have one correct interpretation of what that super simple drawing was trying to say. If we wanted it to mean the other interpretation where the size tolerance did not control the form or the shape tolerance, we have tools in the standard to allow us to put on the drawing to communicate that. So whatever the physical reality is of your design, you can state exactly what that physical reality is by the proper use of this language we call GD&T. So we want our drawings to be to not be able to be misunderstood. You know, we often make drawings and we think, oh, this makes perfect sense to me. And of course it does when you're the one creating the design, because you know what you're after. You know what the thing needs to be. But you assume a lot of things when you make these drawings, and you assume that other people are going to have the same interpretation as what you were thinking in your head. And unfortunately, not everybody thinks exactly the same way. And so we need this standard to be able to communicate this. We need to make our drawings so that they cannot be misunderstood. Here's a simple example. We have a plate with a hole in it, a round plate with a hole in it. How much more simple could this be? I give you the dimensions and tolerances that I need, and we say, there it is. The problem is there's nothing on this drawing other than an implied an implication and potentially an assumption that that hole in this plate is perfectly centered on the OD's center. And of course, ideally, that's exactly where I would like it to be. But there's no tolerance given. Remember, we have dimensions and we have tolerances. The dimension from the center of the hole to the center of the OD of the part is 0 if they're on the same center. But what's the tolerance on that? The plus minus size tolerances on here have nothing to do with the coaxiality, how centered those two features are on each other. The part could come in and look like any of these examples that I'm showing you here, and technically still meet all the requirements of the print. So this part is just as per print as one where the hole is perfectly centered on the OD. We need something to control, to tolerance how centered those things have to be. And everybody says, oh, of course, you know, we would never be off by that much. Oh, well, maybe you wouldn't be off by that much. But technically, I haven't told you how far off it can be at all. Is a micron too much? Is a thousandth of an inch too much? Is 10 thousandths of an inch too much? Is 10 microns too much? The drawing doesn't say. So even though I'm exaggerating it here so that you can see, oh, I mean, legally, technically, that hole could be off of the part completely. And you could have no hole in this part at all and say, yep, I made your parts. And the designer looks at it and says, where's the hole in this thing? Oh, it's off over there somewhere, but don't worry, it's the right size. Okay, I'm joking. But the point is that we're not communicating all of our requirements. We made assumptions about things. And the same thing happens on other stuff like this. We have a plate right here with a little hole in it. And we're saying, here are my dimensions and tolerances of my plate. And it couldn't be any more clear than that, right? This is my drawing up here in the upper left corner. But then when the part actually gets made and isn't perfect, it can have anomalies on it. And we don't know how we're supposed to go about measuring this thing. If I show you with my models here, you know, we imagine this part coming together and just fitting perfectly with its mating parts, and these fasteners that go in here just fitting perfectly, because isn't that wonderful? But then when the part actually gets produced and it's not perfect, and it never will be perfect because we can't make perfect things, the question becomes, do I hold it like this? It looks like I do because that looks like it fits, right? These fasteners actually fit when I hold it like that. But what if I held it like this? Now the fasteners don't fit. I can't get this thing to fit together. The pins don't fit through the holes. And yet I might have measured it this way because I had it set up in my measurement equipment that way instead of this way, and gravity made it go like this. And of course, once again, I'm exaggerating this error so that you can see it with your naked eye. But the bottom line is, that could just be a few microns. That could be a few thousandths. How far off does it have to be, or can it be, before it ceases to assemble or before it ceases to be functional and isn't what I wanted it to be? And so these are the kinds of things that we run into all the time out there in the real world when we're trying to communicate our design requirements to those who have to make and measure the parts that we're after. We have all kinds of ambiguities. Here's another plate with some holes in it. Couldn't be simpler, right? Yeah, well, right up until it comes in and it's manufactured, and I'm going to measure where these features are. Do I measure in the X direction this way, that way? How do I hold it? You know, this is the conundrum that we go through every time we go to try to measure something. And this is why we need this standard. So, we get to this, we understand, okay, there's these ambiguities and we want to overcome these ambiguities. All right. So when should I bother with this GD&T standard? When should I decide to go ahead and invoke this standard on my drawing or in my CAD model? And I'm saying here, there's several instances. Look at the very first bullet point. When part features affect interchangeability or function. All right, now think for just a moment. How many part features do you ever design in your life or make or measure that have zero functionality to the part? I would have to say zero. All of the things that you design and make and measure have features on them that are critical to their function or their interchangeability. So what's the answer to my question? When should you use GD&T? You should always use GD&T. Okay, let me make the question a little bit more generic. When should you use a standardized language to communicate your design requirements from design to manufacturing to inspection and beyond? Always. All right. So we always want to use the standard. Even if we're not using the fancy symbols and whatnot, we still want the rules that come with it, such as the rule that I demonstrated to you with the pin and the fact that the size tolerance controlled the shape of that pin. Okay, what's another reason? Well, when we want to use functional gauges, I have a gauge right here to check this thing. I can put this thing on here and I can see if my pins fit through the gauge and all this stuff. Now, a gauge is an expensive thing, potentially. And we don't want to go spending lots of money on gauges when we don't need to. Okay. But if you want to have the option to gauge your things, using proper GD&T lends itself very well to creating functional gauges. Whether you actually go make a gauge or not is an economic question. All right. It depends on the volume that you're looking at and how much education level the people who are doing the measuring need to have, et cetera, et cetera. But if you want to have the option to gauge things, using proper GD&T lends itself to that to gauging very well. Look at the third bullet point. When datum references are desirable to ensure consistency between design, manufacturing, and inspection. What is a datum reference? Well, quite simply put, it's the same thing I was showing you back here with my models. When I put these parts together and I say, okay, here's a datum reference, here's a datum reference, here's a datum reference, here's primary, secondary, tertiary. I'm instructing you as to exactly how to hold this part to measure where the features are in that datum structure, in that a coordinate system, or what we call a datum reference frame in GD&T. So I'm telling you, I'm communicating to you exactly where my 000 is to then define where all other features have to be. And now you can generate that same 000 and measure, and we're comparing apples to apples. Okay. The last bullet point there is just talking about when your customer requires it. If you have a customer that says you will use GD&T on these on your designs that you send us, then that's what you have to do, obviously. Okay. So now let's also understand the why behind GD&T. When we put tolerances on things, we're telling manufacturing, these are the limits that we can live with from a functional standpoint. If we put tolerances on that are unnecessarily tight, that's going to cost us extra money. Why do we want to spend extra money for something that is that shouldn't cost that much? We want to spend as little as possible to get things that are still functional. So we want tolerances that are as large as they can still functionally be, so that manufacturing has an easier time of making them and therefore charges us less money to do it. We want to save money. Everything always comes down to money, right? And we have to communicate these tolerances in a clear and understandable and unique way so that everybody up and down the line understands exactly what those tolerances are and how to check them. We need to be able to check them, inspect them consistently. Okay, so the why behind GD&T is because it saves money. It gives us the ability to put on our designs the maximum possible yet still functional tolerances. And that's what we need to make things work. It ensures that design requirements are carried out. Okay, it's not threatening anybody with bodily harm if they don't achieve your design requirements, but it is giving us the ability to communicate exactly what our design requirements are. If we know exactly what our design requirements are, we have a much better chance of achieving them. It ensures interchangeability. Okay, that statement depends on the design person actually doing the math and actually doing the tolerance stacks and making sure that the things actually will fit together if you make them within these limits. But it gives us that ability to state what those limits actually are. So we say, if you make it per print, it will fit together with this mating part. Provides a common language. I don't care what your native language is. Obviously, my native language is English, but you don't have to have English as your native language to understand GD&T. So as long as you understand GD&T and I understand GD&T, what our native language is irrelevant because we can communicate our design requirements using the GD&T, our common language. It saves time. Well, it doesn't save time yet because you're sitting here looking at a training video or a training session and you're not at your regular jobs doing your regular things. So it doesn't save time immediately. It's an investment to save time in the future. It's going to reduce the number of engineering change notices that you have to have. That's ECN on there. It's going to improve communication, not just the written communication on your drawings, which it does do, but in addition to that, we can speak this GD&T language and communicate more succinctly what our requirements are. In the US, the Department of Defense requires that you use it. That was one of those ones where I say if your customer requires it. All right. And the other advantage of using GD&T is that it uses symbols to communicate. So once again, overcoming these language barriers, the symbols only mean one thing. Once you know what the symbols mean, that's what they mean forever. And we can put these things right on the model or right on the drawing, right where they apply, not off in some notes someplace that somebody's going to misinterpret anyway. Okay. And these symbols are all compatible with your CAD systems, which makes them compatible with downstream technologies like measurement equipment or CNC machining, et cetera. I'm going to do a really quick example here of a drawing with notes that uses GD&T concepts, but using notes to convey those concepts. Then I'm going to I'm going to show you the same drawing with GD&T to convey those concepts. So look at this real quickly. We have a surface we want to be flat within 0.1, and we want it to be called datum A. And we have a surface over here that's datum B, and we want it to be it's got a flag note there, and the flag note says surface B has to be perpendicular to datum A within 0.1. Once I totally understand what that means, I can do what it takes in the shop floor to achieve it. I can do what it takes in the inspection department to inspect it. I've got another surface here, datum C, and that's got a flag note with it, and that one says surface C has to be perpendicular to datum A within 0.1 and to datum B within 0.1. And again, if I know what that means, I can do what it takes to achieve it on the shop floor. I can do what it takes to inspect it. This word basic in GD&T means theoretically exact. So all these dimensions are theoretically exact. If the world were perfect, these holes would be exactly at these basic dimensions. But we know that you can't make perfect things. So we have to tell you how far off of perfect is still okay. We have to set those limits, right? So we tell you up here, the holes have to be this big within this much. That's the limits on the size and the form. And then they have to be on those theoretically exact positions within a 0.3 diameter zone. So we're giving you a bullseye that's 0.3 diameter at each one of those hole locations, ideal hole locations, and your actual as manufactured hole has to have its axis contained within that zone that's 0.3 in diameter. That's a lot to take in notes, and I'm not sure everybody would have that same interpretation, but if you put it in GD&T language, it's defined in the standard, so there's only one correct interpretation. So what did the drawing with the note say? It said this surface had to be flat within 0.1, and we wanted to call it datum feature A. What do you suppose this symbol means? I'll tell you, it's flatness. And it says flat within how much? 0.1. That's what the note said. And it's attached right here to the extension line coming off the object line that is our surface in question. And so this is saying that surface must be flat within 0.1. That is the limit of how out of flat it can be. And oh, by the way, we're naming it datum feature A. This surface over here was datum feature B, and we said that surface had to be perpendicular to datum feature A within 0.1, and that's what this GD&T sentence says. So I didn't have to have it off on some note in some other page somewhere. I didn't have to read the notes and try to understand what the notes meant. I just have to understand what these symbols mean, and I know exactly what's being communicated. And this third surface here, we called it datum feature C, and we want it to be perpendicular within 0.1 to both A and B, and that's what this GD&T sentence says. Then we had these theoretically exact or basic dimensions, but instead of writing the English word basic next to each one of them, we just put a box around it. That's the symbol we use to communicate that theoretically exact dimension. Now, again, we know that you can't make perfect things, so we have to tell you how far off perfect you can be. So we wrote you this paragraph up here. We just wrote it in GD&T language now instead of English, and it just says the holes have to be this big within this much. That controls their size and form, and they have to be on those theoretically exact positions within a 0.3 diameter tolerance zone. Let's forget about what this MMC symbol means, but if this were a longer class, I could come back and teach you all about that. But suffice it to say, it's functional for the fit of this design, and it's relative to A, B, and C. So it says the same thing that the note said, but it says it in GD&T language. And once you understand that language, you can read it just like you read your native language. It's no problem. And this is defining these tolerance zones, and these tolerance zones are theoretically exact. They're imaginary, so they can be. The axis of the as manufactured hole has to fit somewhere inside that zone. So I say, what goes in the tolerance zone? In this context, it would be the axis of the holes. So each hole's axis has to fit within its respective zone throughout the length of that feature in order to be per print. And that will ensure that this part will fit together with its mating parts. And the standard comes with all sorts of symbols that we can use to communicate all sorts of requirements, whatever they happen to be. You just have to go through the training to understand it. And once you understand it and are fluent in that language, now you can communicate with GD&T. That's the who, what, why, where, and when of geometric dimensioning and tolerancing. Thanks for joining us. I appreciate your time. We hope to see you sometime in the future with one of our recorded classes from Tata Technologies and I Get It, or from AGI directly. Thanks again, and have a great day.
Thank you, Mark. Thank you for the GD&T session. Let's now move to question and answer portion of the webinar. At this time, please type in your questions into the chat for Mark to answer.
I see somebody did ask, as a mechanical engineer, how will this help us? I hope I addressed that in what I said. You know, there are so many times when we put on a drawing something that we think is perfectly clear, and somehow somebody downstream interprets it in a different way, and suddenly we're either accepting parts that aren't working or we're rejecting parts that would work. And how can that not help you? It's going to reduce your erroneous rejects. It's going to reduce your scrap. It's going to, you know, it can only help you. That's what it's designed to do. That's the whole purpose of the standard itself, is to communicate better so that we don't have those misunderstandings. What other questions do we have?
Anyone else, please type in your questions. I guess we'll give it a few more 30 seconds or so. Yeah, a countdown.
Well, I hope that I addressed a lot of your curiosity of what geometric dimensioning and tolerancing is, and I hope that I did point out some of the advantages of using it. It is a language, and you should treat learning it like you would treat learning any language. It's not good enough to just dabble with it. You have to get fluent with it if you're going to actually be able to communicate effectively. Somebody just asked the question, how does GD&T handle color during anodizing? GD&T is about dimensions and tolerances of physical dimensions. So it does not address color or anything like that. That would have to be covered under other standards other than Y14.5. Somebody asked the question, what is bonus tolerance in GD&T? I alluded to it there real quickly, but because the session is so short, I didn't go deep into it. But essentially, it's a recognition of the physical reality when we put things together. Like, for example, put pins through holes in something with clearance. It's a physical reality that the more clearance there is, the more room you have to place the hole or the features, and, still get them to fit together. That's just a physical reality. If I've got this part that I keep playing with here, and I'm putting this thing through here, and I put pins in there. If I make the holes bigger, then there's more room to move the hole around in terms of its location to still get the pin to fit through. That's a physical reality. That's not GD&T inventing that. That's just real. That's just the truth. And GD&T just has the ability in the language to give us tools to say when that physical reality is our physical reality for our design. We can put that symbol on there, and then that allows you to use this extra tolerance that physically exists. So is maximum material condition, least material condition, regardless of feature size, are the modifiers that we can put on things. And those are the tools within GD&T that we can use to communicate that bonus tolerance is physically available.
Any other questions, anyone? No?
It takes a lot longer than 30 minutes to learn GD&T, just like it would take a lot longer than 30 minutes to learn German or Spanish or French, right? So that's why I say treat learning GD&T just as you would treat learning any other language. It's just that the only difference between GD&T and any other language is that it's standardized and it's technical. So you're trying to communicate technical requirements about the dimensions and tolerances of the things that you're designing or making or measuring. And GD&T is the language to get that done.
Okay. Well, thank you again, Mark, I guess we'll just go ahead and move on. Thank you again for answering the questions. Appreciate it. Great job. And let's see, I'd like to thank, let's go ahead and move on to the next slide. I'd like to thank everyone for attending today and attending the webinar. Be sure to look for an email with a special 7-day offer. This is for everyone who attended today's webinar. And for more information, please visit us at myigetit.com. And for any other questions concerning iGetIt subscriptions, please contact us at support@myigetit.com. Also, be sure to look for more webinar sessions here at iGetIt. We will have another webinar live session in 2 weeks, so please check your email inboxes. And have a great day, everyone. Thank you.